Hello everyone and welcome to Frogs, Fleas, and Painted Cubes 1.2. Our learning target today is I will be able to correctly create the maximum area of a rectangle with a fixed perimeter using a graph or table. Today's ACES questions are 3, 5, 18 through 31. So as we take a look here, below you'll see a graph from problem 1.1. This is what you used in the last problem. Excuse me, and as it's labeled below, the shape of this graph is called a parabola, and this one opens downward. The opening is facing down. In this graph, the area, or our y-axis, is a function or dependent variable of the length. Now I'm going to throw up here another parabola that we will be using here in problem 1.2 that you'll be using tomorrow in the classroom. So both of these graphs represent the area of a family of rectangles with a certain fixed perimeter. I want you to take a look at these two and be able to pause the video here and tell me how are the graphs similar and how are they different, and write those down. So go ahead and pause the video now, write that information down. So as we turn to page 9 in our textbooks, reading graphs and tables, we have some vocabulary we need to go over here. It says a relationship between length and area in problem 1.1 is a quadratic function. And if we look to define quadratic function, our book tells us that a function between independent and dependent variables such that as the dependent values increase by a constant amount, the successive first differences between the dependent values change by a constant amount. So it's going to give us an example of y equals x squared. Each time we increase x by 1, the first differences for y are 3, 5, 7, 9. Meaning if we put 1 in for x, 1 squared is 1. If we put 2 in for x, 2 squared is 4. The difference between 4 and 1 is 3. If we put in 3 squared, that's 9. 9 minus 4 is 5, and so on and so forth. Then the second differences are 2, 2, and 2, meaning there's a difference of 2 from 3 to 5, 5 to 7, 7 to 9, and so on. The graphs of quadratic functions have the shape of a U or upside down U with a line of symmetry through a maximum or minimum point on the graph that is perpendicular to the x-axis, and you'll see that here in a minute. Quadratic functions are characterized by their U-shaped graphs, which are called parabolas. So if we go back to our vocabulary and we see parabola, this is the graph of a quadratic function. The parabola has a line of symmetry, which they're pointing to here, the red line going up and down, that passes through the maximum point if the graph opens downward, that would be this point here, or through the minimum point if the graph opens upward, that would be this point here. And as you see, the line of symmetry splits the parabola in half. Okay. Problem 1.1, the area depends on or is a function of the length. Recall that a relationship in which one variable depends on another is a function. Because the variable area depends on the length, it is called the dependent variable. We have seen dependent variables in the past, such as in our y equals mx plus b. Y is dependent on x, or the independent variable. The variable length is the independent variable. So area is dependent, length is independent. We've studied other families of functions in earlier units, and if we look at them, we've had our linear function, and that's a distance covered by a van traveling at a constant speed as a function of time. The relationship between time and distance is a linear function, similar to y equals mx plus b. We've also done inverse variation, where the time needed for a van to travel a set or constant 200 miles is a function of the average speed of the van. The relationship between time and rate is an inverse variation. So we had our constant equals speed times our time times rate. Okay? And then finally, our exponential functions that we just did. The value of an investment that grows at 4% per year is a function of the number of years. The relationship between the number of years and the value is an exponential function. So A would represent the amount of money we put in at the beginning, or our y-intercept. B is our 4% growth rate, and then X is our number of years. So these are all relationships that we've been working on so far, and now we're getting into quadratic functions. As we take a look at problem 1.2 on page 10, when you get into this, I really want you again to pay attention to patterns and different things that you see like that can help you out. Okay, we're going to be using this graph here that you saw a couple of slides earlier. Again, it's a rectangle with a fixed perimeter. Area is our independent or is our dependent variable, and length is our independent variable. I'm not going to go through and read all of these to you. This is mostly observation for you to be able to read the graph and determine some things and find some patterns. But I do want you to answer all these questions, and I want you to have good discussions with your teams in the classroom. But before you come to class, please read through these, get an idea of what you think your answers might be so that you can have a good open discussion with your team. As we go on to the second part, part B, now we've been given a table, and it's asking you very similar questions to what was asked back here for the graph. So it wants you to be able to read both a graph and determine what the answers are, as well as being able to read a table and determine what those answers are. Once you finish those two, take a look at part C. And I really want you and your teammates to talk, discuss, disagree, and come up with ideas and patterns that, based on questions A and B, describe the change in area as the length increases by 1. So as our independent variable increases by 1, how is that affecting our dependent variable? And then compare this pattern of change to those for linear and exponential functions and for inverse variation. And again, in case you've forgotten some of that, I've given you the different types of equations back here. So go ahead and try to determine how, when we change 1 unit of length, how does that affect area, and compare that to the other types of equations and functions that we've already gone over so far this year. So that's problem 1.2. Again, the ACES assignment for that is going to be 3, 5, and 18 through 31. Look forward to seeing your investigations and listening to your discussions and hearing your questions in class.